Welcome to section 14.6. In this section, we will be talking about the concept of directional derivatives and the gradient vector. So we have been working so far with the partial derivatives of a function with respect to x and with respect to y. That's fx and fy. So we know that these partial derivatives represent derivatives in the direction of x and y, but what we are trying to do is not just take derivatives in those two very specific directions, but we want to be able to take derivatives in any direction. So in order to do this, we say if f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u equals ab, and we get d sub u of f of xy equals fx of xy times a plus fy of xy times b. So if we have a differentiable function, we can take the derivative of that function in any specific direction, so the direction of this unit vector, using this process. Now, we're going to work on rewriting this a little bit to come up with kind of a nice clean formula that relates to the topics we've talked about already. So notice with this formula, if the unit vector that we're working with is just the I vector, so 1, 0, then the directional derivative of the function we would have, so 1, 0, so this would be a 1 and this would be a 0, so this would all be gone. We would just be left with fx right, which is the derivative of x in the derivative of f in the x direction, which is exactly what I is, right? It is a unit vector in the direction of x. And then similarly, if the unit vector is j, then our directional derivative would just be fy. So this tracks with the couple of partial derivatives that we know already. Now, let's play around with this theorem a little bit. Try to get this into a form that looks a little more familiar, like something that we have worked with before. So, directional derivative is fx of xy times a plus fy of xy times b. Notice if we consider the partial derivatives and then we consider the a and the b, because ab is coming from that unit vector, consider them to be kind of separate objects. Think of them as vectors. If we had this times this plus this times this is the general format of a dot product. So if we considered a vector with fx and fy in it, we could dot that with a vector ab. That vector AB is just the vector u. That's this unit vector from back up here. So we're going to have this vector with fx and fy dotted with u. Now, this vector whose components are the partial derivatives, so fx and fy. This vector occurs so frequently that it gets its own name and its own notation. So if f is a function of two variables, x and y, the gradient of f is the vector function whose notation is going to look like this. So we've got like an upside down triangle here. F of xy equals the vector whose components are fx and fy. Okay. Or alternatively, we can kind of mix and match notations here, just so that we know that these are all equivalent to each other. Okay, so instead of saying the gradient of f every single time, we typically abbreviate this as grad f. Or sometimes you'll see it as del f. Kind of like this, like if we had a fully upright triangle, this would be delta. It's kind of like that, so we call it del. So if you hear grad f or del f, that just means the gradient of the function, okay, which again is just a vector whose components are the partial derivatives of that function. So let's try an example. Find the gradient vector for this function and evaluate it at the point 0, 1. So the gradient, so grad f of xy, we're going to have a vector, and this the gradient isn't really asking us to do anything new or different. It's just asking us to take the same partial derivatives we've been doing for several sections now and just put them into the components of a vector. So we take the partial with respect to x, we're going to get cosine x plus e to the xy again times the partial derivative of xy with respect to x. So we're taking partial with respect to x of this, which means we differentiate the x, which gives us a 1 times the y. So it looks a little weird maybe to see it written this way, but the partial with respect to x is actually y e to the xy. Okay. Again, because the derivative of the x became 1. And then partial with respect to y, this is a 0 because there's no y's. This one, by a similar reasoning, is just x e to the xy. So that is the general gradient, and now it wants us to evaluate it at the point 0, 1. So that's cosine of 0 plus 1 e to the 0, and then 0 e to the 0. So that's 1 plus 1, so 2, 0. So we have, for the given function f, at the given point 0, 1, the gradient, okay, which consists of the partial derivatives fx and fy, would be the vector 2, 0. All right. So when we're talking about the directional derivative, instead of writing the vector of fx of xy, comma, fy of xy every single time, we just write grad f. So directional derivative is going to be grad f of xy dotted with u, that unit direction vector. So let's try one of these out. Find the directional derivative of this function at the point 2, -1 in the direction of the vector 2, 5. So we can go ahead and get the gradient first. So we're going to have 2xy cubed, and that's it. And then for fy, we get 3x squared y squared minus 4. Now we want to evaluate the gradient at the point. So at the point 2, -1. So that's going to be, so grad f of 2, -1. So that's 2 times 2 times -1. So that's -4. And then 3 times, that's 4 and +1. So that's 12 minus 4 is 8. So that's the gradient vector. And we want to dot it with the direction vector. However, remember that the direction vector has to be a unit vector. Now, why does it have to be a unit vector? Well, because we're trying to find a derivative, which is a numerical value, right? It gives us the slope of a function at a point in a specific direction. If this is not a unit vector, its length is actually going to scale up the value of the derivative, or down if it's less than a length of 1. So like if this had a length of 10, then our derivative would be 10 times higher than it should be at that point. And so we need this to be a unit vector so that we're just essentially multiplying by a length of 1, and it doesn't scale up or down the slope or the derivative. So recall, direction vector must be a unit vector. So we need to go ahead and get the length of this vector v. So that's square root of 4 plus 25. So we get rad 29 for the length of this vector. So to get the new vector, so u will be 25 over rad 29. So that's 2 over rad 29, comma 5 over rad 29. So this will be the unit vector that has the same direction as v, but now has a length of 1. So we can go ahead and now compute directional derivative of f of xy. So it's going to be the gradient at the point dotted with our unit vector u. Okay. And we should never assume that the vector that's given is a unit vector unless the problem specifically says that it is. So don't just assume that this is a unit vector. We should always check to be sure. So let's see here. So we've got the gradient dotted with the direction vector. Okay, so we multiply corresponding pieces, so we get -8 over rad 29 plus 40 over rad 29, which is 32 over rad 29. So that is the value of the directional derivative. So that is the slope on this function at this point in this direction. Okay, that's the slope on this function at this point in this direction. If we changed the direction, the slope would be different. If we changed the point we were at, the slope would be different. If we changed the function, the slope would be different. So this is a very unique value, okay, that is specific to this function, this point, and this direction. And again, just to bring this back one more time, that unit vector did play a role in this final answer. If you didn't have it as a unit vector, you would have just gotten 32 for the final answer. And we're kind of trained that when we see like a whole number in a solution, it looks really nice, like in a textbook or something. And so maybe we don't even question that that's the right answer, but 32 would have been way too large by itself. So we needed to divide by that rad 29 to get the actual directional derivative value. In functions of 3 variables, we have the same concept. So grad f of x, y, z is fx, fy, fz. So just like so many things in this class, it's the same, just with one extra variable. And our directional derivative is the same formula, but with 3 components instead of 2 in the vector. Now, an interesting property of the gradient and the directional derivative, the maximum value of the directional derivative occurs when u, that direction vector, has the same direction as the gradient vector, grad f. So if the direction vector that we're working with points the same direction as the gradient, that is where the maximum derivative will occur, or the maximum slope at that point will occur in that direction. This maximum value itself is the magnitude of grad f. So again, if our gradient and our directional vector are pointed the same way, that will maximize our slope, our derivative value, and that maximum derivative is whatever the length of the gradient is. So we can actually prove this. It's kind of a nice, simple, concise proof for us. If we take a look at directional derivative of f, that's going to be grad f dotted with u. And we know from properties of the dot product, there's a special formula that relates these together, and that is the length of the first vector times the length of the second vector times cosine of theta. So again, this is a dot product property from a couple chapters ago. We know that this relationship is true. We also know that u is a unit vector. So it has a length of 1. Okay, so this whole thing is just 1. So all that's left is length of f times cosine of theta. Now, the length of the gradient of f is going to be whatever it is. The cosine can change depending on what theta is. So if we think about the possible values that cosine can take on, cosine oscillates, right, between -1 and 1. So this is maximized when cosine theta equals 1. And what value makes cosine 1? So which occurs when theta equals 0. So this will be maximized when cosine is at its maximum, which is when it is 1, and that occurs when theta is 0, or in other words, the angle between grad f and u is 0, or in other words, they're the same direction, they are parallel. Okay, we can say, so the angle between grad f and u is 0. Thus, they are the same direction. So the maximum value of the directional derivative occurs when the angle between grad f and u is 0, or in other words, they're pointed the same direction, or they're parallel, however you want to think about that. And the value itself, so we can say, and the maximum value is when cosine of theta is 1. So that's magnitude of f cosine of 0, which is 1, which is just the length of the gradient, which is exactly what we set up there. So that would complete our proof. So again, maximum slope, maximum rate of change occurs in the direction of the gradient. So that tells us the steepest slope on the function at that point. By a similar token, you can also prove that the minimum slope, so going the lowest value or possibly the most negative, if it is negative, is in the opposite direction of the gradient. So if we took it the exact opposite way, so instead of it pointed here and here at 0, if we had one pointing this way and one pointing that way, so like at an angle of pi, right, all the way around here, that would minimize the slope or the derivative at that point. And that's also something that we could prove, but it works out just like this one does. So let's take all of these things together and try out another example. We have a function, x e to the y. Find the rate of change of f at the point 2, 0 in the direction from p to q, which is 1/2 comma 2. And then it's asking what the maximum rate of change is and in what direction it's going. Okay. So we have the function. We're going to need the gradient. So let's go ahead and just set that up first. So we've got grad f of xy. Let's see. So with respect to x, that's just a 1 out in front. So that's just e to the y. With respect to y, the x tags along. So it's just x e to the y again. So no change on that one. Now we want the gradient specifically at the point 2, 0. So we'll go ahead and substitute that in right now. So that's e to the 0, comma 2 e to the 0, or 1, 2. So the gradient of f at the point 2, 0 is 1, 2. Now we need to dot this with a direction vector. We don't have a direction vector, but we know that it is in the direction from P to Q. And if we know 2 points, we can create a vector between them. So this is throwing it back a bit to some of our earlier chapters, but we can create the vector PQ simply by taking terminal minus initial, by subtracting. So we would get 1/2 minus 2, comma 2 minus 0, which is negative 3/2, comma 2. And again, we can't assume that this is a unit vector, so we need to go ahead and find the corresponding unit vector. So that's negative 3/2, comma 2, all over square root of each of these squared. So that's going to be 9 over 4 and 4. So let's see, we've got negative 3 over 2, comma 2. Over 4, that's going to be 16 over 4 right there. So combine those, that's rad 25 over 4. So that's pretty nice. It works out to a perfect square here. So that's going to be 5/2. So if we divide this by 5/2, that's the same thing as multiplying by 2/5, like that. So multiplying by the reciprocal. So we can go ahead and multiply. We would get negative 3/5. And multiply that, that gives us 4/5. So that would be our unit direction vector. So it's pointed the same direction as this one, but it has a length of 1. And if you're not entirely sure that you did it correctly, you can always go back and find the length of this new vector, and you will see that its length is 1, and so we can use it. So, directional derivative of f at the point 2, 0 is grad f dotted with u so we get negative 3/5 plus 8/5 combine is 5/5 or just 1. So we end up just getting 1 for the value. That is the slope. So that is the rate of change of this function x e to the y at the point 2, 0 in the direction from 2, 0 to 1/2 comma 2. So that is our slope. Now for part B, what is the maximum rate of change of f, and in what direction does this occur? So the maximum rate of change, we're going to take the magnitude of f, of grad f, also at the point 2, 0. So this is the magnitude of the vector 1, 2. So that's square root of 1 plus 4 is rad 5. So this is our max rate of change. And it is in the direction of the gradient vector. So in the direction of the vector 1, 2. So this is a value that's a little bit more than 2. So right now, we are not pointed in that specific direction of the gradient, right? We kind of moved around a little bit by dotting these together. We got a slope of 1. The largest the slope could possibly be at this point would be rad 5. And that would be specifically if we were in the direction of the vector 1, 2. Anything else would have a value lower than that. Okay. And this is how we find the gradient vector, how we find a directional derivative, how we can identify maximum rate of change and the direction as well. You'll see down below that there's a section, a little piece about tangent planes to level surfaces. We're not going to get into that for this course, so you don't have to worry about the bottom half of this page. We're just going to stop here for the section, and that brings us to the end of section 14.6. So I will talk with you all very soon in the next section.